Welcome to the session of Cryptanalysis and Arithmetic-Oriented Schemes. This session has 3 talks, and the first one is more vulnerabilities of linear structure S-box-based ciphers reveal their inability to resist DFA. The authors are Amit Jana, Anup Kumar Kundu, Gautam Paul, and the speaker is Anup Kumar Kundu.
Hello. Hello. Thank you, sir. So today I will present our work on more vulnerabilities of linear structured S-box-based ciphers reveal their inability to resist DFA. This is a joint work with Amit Jana and Gautam Paul from ISI Kolkata. So initially I will talk about default. So default is the first attempt to design a DFA immune cipher at algorithmic level. Here it has 3 layers: default layer, default core, and again default layer at the last. So both default layer and default core follows the SPN structure. Default layer uses linear structured S-box and default core uses non-linear S-box. So linear structured S-box I will talk about later. So here designers initiate the cipher as gift-like structure. It has actually 2 versions. The initial version, or it might say like the simple key schedule. So in initial version, each round key, in each round the 128-bit round key is used, and in the modified version there are 4 independent round keys, say K0, K1, K2, K3, which is used in 4 consecutive rounds. So this is a gift-like structure where each round consists of S-box layer, permutation layer, add round constant, and add round key. Default has state size and key size of 128-bit. It has total 80 rounds, 28 default layer and 24 default core. So because of that 2 into 28, that is 56 plus 24, that is total 80 rounds. So each round has S-box layer, bit permutation, add round constant, and add round key. On the other hand, we have bakshish, which is also similar structure as like default, but it has 35 rounds, and in each round key, suppose Ki is a round key, in the next round the round key is rotated, circularly rotated by 1 bit and used as the next round key in the next round. So linear structure. So for normal S-box, we have for any point A, the probability of suppose A to B, like suppose we are giving a difference A, then and we are getting a output difference B, then the probability of A to B is something like 2, 4 or something. But for 0, like if the input in the DDT there is only 1 point, 0, for which the same input difference goes to same output difference. But for linear structured S-box, there are some other non-zero values, say A, for which f of x XOR A equals to C. So default has 3 LS, that is it has 3 non-zero points for which the same input difference goes to same output difference, and bakshish has 1 LSS box. So for default, for any round, the total key space got reduced to 2 to the power 64. So nibble key space got reduced. If we apply differential fault attack, then for one fault the key space, nibble key space will reduce to 2 to the power 2 from 2 to the power 4. So in total 2 to the power 64 for each round. For bakshish, this total this after applying one differential fault attack, the total round key will be reduced to 2 to the power 32. So if we see the DDT of default layer and bakshish, then we can say without 0 there are other points like 6, 9 and F, for which we can see 16, the value 16. So if the input difference is 6, then the output difference will be 9 for default layer. For n, if we vary x from F to 4. For bakshish there is only 1 point, and because of that for default the total it has 3 LS because it has 3 points where 16 appears without 0, and for bakshish it has only 1 point, so because of that it is 1 LS. Now QR structure of gift permutation. So gift permutation, the bit permutation layer of gift has a unique property which has the total 128-bit permutation is divided into 8 16-bit permutation. So total 16-bit are permuted to 16-bit in the next round. So it has 8 many such bit permutation, 16-bit permutation because of that total 128-bit permutation layer. So the advantage of this is the key space of 2 consecutive rounds can be splitted according to the key space of the QR groups, and for that we don't have to guess the whole round key at once. We can guess the round key of the QR groups, and after that we can apply the Cartesian product of the round keys, reduce round keys, and get the original and get the total possible master key, possible keys within which the master keys will be one. So now attack procedure. So there are some other works on the cipher. First is Nagalar et al. They have first showed a DFA for all key schedules by combining information through rounds. They expanded in their attack their DFA by inducing bit flip-flops across multiple rounds to further reduce the key space. Their strategy involves injecting differences at certain rounds and exploring all possible differential paths through the subsequent rounds on DDT. Because of that, the key space got reduced to 2 to the power 20 by using 16 faults. We have verified that if we increase the number of faults, then also the key space does not reduce to 1. At most it can reduce is 2 to the power 16 or 20. Now another work is by Day et al. They have applied DFA on simple key schedule to reduce the key space to 2 to the power 16 by using 112 faults. And their attack does not apply on the rotating key schedule, which is the updated one for default. So our contribution, we have introduced a novel technique to compute intermediate differential trails uniquely because of fault. This leads to reduce the key space even faster. This significantly reduces the number of faults when the faults are injected at the 5th last round. For gift-like permutation, we devise an algorithm to compute unique trails up to 5 rounds using gift keyword structure for default. For Bakshish, it has like 3 rounds. So suppose initially we are giving a fault at our ith round at the 0th nibble. Suppose the rightmost nibble is the 0th nibble, and in the red colored bit we are inducing the fault, and because of that the total after 3 rounds we are getting the output difference at the red color bits at Ri plus 2. So here we will use the QR group structure strategy, like we are taking the 0th remainder group of Ri plus 1, which is colored where the bits are colored in blue. So for default the linear structured S box has 3 LS. So for each output difference there will be fixed 4 input difference. So we will combine the input differences of the remainder group of Ri plus 1. So there will be 2 to the power 8 such. We invert the combined difference at Ri plus 1, and then we take the input difference which is occurred at Ri, and we check all the possible output differences, and we apply the permutation layer and check that what will be the possible output difference at the input of Ri plus 1. Depending upon that, we will reduce the we will get the possible input difference in Ri plus 1 in the quotient group of Ri plus 1, which is this. So if we apply the same technique for all the other quotient remainder groups of Ri plus 1, then we can again reduce the then we can get the possible input differences for all other QR groups in Ri plus 1. And if we apply the same technique in the upper round, that is in the round Ri, then the total we will get the unique trail for 3 rounds. So by this procedure we will compute the unique trail for 3 rounds. So now we will try to find out the trail for 5 rounds. So for 5 rounds we will apply a particular property of gift-like structure, which is if we give the fault at the nibbles 0 to 16, which is the rightmost nibbles for this case, which are colored at red. So after 3 rounds we can see that there are fixed 64 bits where the difference can spread after 3 rounds. So if the difference is given at from 16 to 31st nibble, then after 3 rounds the total bit after 3 rounds we will get the bits, the difference at the bits which are colored at blue. So we will use this property to recover the trail, unique trail for 5 rounds. So for 5 rounds, suppose the difference is given at the particular highlighted nibble in Ri minus 1, and after that we will get the we are getting the output difference at Ri plus 4. So here also we will use the same strategy, like we will first choose the keyword group, 0th keyword group of Ri plus 3, and then which are highlighted as blue. So we will take the possible input differences and we invert the input differences and apply the inverse bit permutation layer to go to the down of the S box layer in Ri plus 3. Then we check that whether if we apply the inverse S box operation, then also the difference appears in the green highlighted bits or not, which is the actually 3-round property of gift permutation layer. Depending upon that, we get the unique input difference at Ri plus 3. So if we apply the same strategy for other keyword groups, then we can get the other input differences for other keyword groups, and by combining those we get the total possible input output differences for the last 2 rounds. Now we apply the 3-round trail strategy that I discussed earlier. So using that we can get the unique trail for 5 rounds. So now the key recovery attack. So in the attack procedure, as we have the unique input output bit difference for each nibble, here we reduce the key space of each nibble of Ri plus 4, which is the round of the last round, which is the last round for each input output difference from the ciphertext. We combine the key space of Ri plus 1 for each quotient group of Ri plus 3. Then we combine the key space of all even nibbles in Ri plus 4 to filter at least all the least significant 16 nibbles. Then we apply the input output bit difference for round 4 and 5 to get the whole reduced key space in Ri plus 4. So using this strategy, by using total 5 faults, we reduce the total key space of 1 round by 1. So we can uniquely recover the total round key for default layer. So attack on rotating key schedule. So Gift has actually rotating key schedule, which is 4 independent round keys K0, K1, K2, K3 are used in 4 consecutive rounds in default layer. As default has 3 LS, so the LS is 069F, so there exists fixed input output difference alpha beta for which the probability is 1, which we have seen from the DDT. So for any alpha belongs to LS, there exists beta belongs to LS inverse such that S of X XOR S of X XOR alpha equals to Sx XOR S alpha. Now if we define the set L of X comma S inverse, which is alpha beta, then if we consider the toy cipher y equals to S of XOR X XOR K naught XOR K1, then if K0 comma K1 is an actual key, then for any alpha beta K0 hat comma K1 hat, which is K0 XOR alpha comma K1 XOR beta, will also be an equivalent key. So the equivalent key is, if we use the equivalent key, then the same input difference will lead to same output difference. So for a round key pair K0 comma K1, there exists 2 to the power 64 as it has 32 S boxes in each round, such equivalent keys which will satisfy the same input output difference. So in the below there is a original key and a equivalent key example. So attack strategy, we divided the attack strategy in 4 parts. So initially from key space to equivalent key space, we give 32 faults at 5th last round, so that at each round 2 distinct input output differences got generated at last, second last, third last and fourth last. So we compute K3 hat, K2 hat, K1 hat, K naught hat by using 5-round trail strategy for last 4 rounds. This reduces the total key space of each Ki to 2 to the power 64. Now after that we will get the equivalent key space. So for in equivalent key space, for each input difference, this will lead to unique, for each key the input difference will lead to the same output difference. Now we will find out an equivalent key. For this we give 4 faults at 10th last round. We use Ki hat for Ki equal to 1 to 0 to 3 to recover the unique trail for 10 rounds. That is, we invert from last round to fifth last round, and from fifth last round to 10th last round, we apply k1 hat, k2 hat, k3 hat, the unique the values of k1 hat, k2 hat, k3 hat, and all possible values of k0 hat, which is 2 to the power 64, and use our previous attack procedure to get the unique value of k0. So that will be k1 hat, k2 hat, k3 hat, and k0. That will lead an equivalent key. That is, if we apply the same input, it will lead to the same output. So to get the original key, if we have to inject the fault at default code and recover its original key with less number of faults. So the results are total 36 faults are needed to reduce the key space of default layer. For default code, 36 faults were needed to reduce the key space of default layer. For default code, 32 faults are required to recover the key uniquely after giving the faults at second last round. So SDFA. In SDFA, we have combined the traditional strategy of differential fault attack and statistical fault attack by using bit set faults. So our objective is to identify the common nibbles values that passes through both DFA and SFA. So in SFA, we are setting a bit and we are checking the output difference and depending upon that, we reduce the key space. So if we understand this by an example, so suppose we are giving input output difference 2 to 7 by using a bit set fault E1 equal to 1 in an S box. Now if we use a DFA, then the total key space will reduce to this. If we use SFA, then the key space will reduce to this. So if we apply both the properties SFA and DFA, so by using SDFA, the total key space reduces to 5S78, which is by using one fault only, the total key space will reduce to from 2 to the power 4 to 2 square. So using this, for default, 64 to 128 bit set faults are required to reduce the key space to the unique one. So the results on Bakshish are similar attack we can apply on Bakshish. For Bakshish, minimum 2 faults are needed in each nibble to reduce the key space, nibble key space to 1. In the worst case, for Bakshish, 128 bit set faults are needed for unique key recovery. So this is the result of Bakshish, where we can see if we give the fault at third to last round, 12 number of faults are needed to recover the unique key for Bakshish. So this is the summary of our results. So here we can see that for the fifth last round, 5 faults are needed. For in the rotating schedule, 36 plus X fault are needed, where X is the number of faults that we have to give at default code. For Bakshish, 12 faults are needed to recover the unique key. So conclusion is our approach involves constructing deterministic differential trails up to 5 rounds for default layer and 3 rounds for Bakshish. For simple case schedule, we demonstrate that approximately 5 bit flip faults are sufficient to uniquely recover the key of default for default layer. For rotating key schedule, we showed that approximately 36 bit flip faults are required to recover the equivalent key of default layer. In this paper, we have introduced a novel attack procedure called SDFA, which combines both SFA and DFA. We applied our proposed DFA attack on Bakshish, which and efficiently recovered its master key. This requires 12 faults to recover the unique master key. Finally, our findings underscore the difficulty in achieving DFA protection for linear structured based S box. So, thank you.
Thank you for the talk. So, is there any questions from the audience?
Thank you for your talk.
Thank you.
So the question is, did you find your attack by using some tool, or did you find it by hand? Or in general, can you comment on the optimality of your attack?
Optimality means in which sense you are?
If it's possible, potentially the attack can be improved by future.
Okay, so this attack procedure can be improved or not, or okay. So yeah, but like we have checked that whether we can, as for default layer, we recovered the unique trail for 5 rounds. So initially we have tried that whether we can get some more number of rounds, unique trails for that. So, but the problem is we have to get some property, like for default layer, as after 3rd rounds, for gift permutation, we found a property which is after 3 rounds there are some fixed nibbles where the difference will propagate. So using that we recovered the total 5-round unique trail. So we cannot get the unique trail after that, or we cannot get the property for more number of rounds, using which we will get the unique input-output bit difference. So if we can find any property for 4 rounds or after that, then we can improve obviously this. Or you might say that using our attack procedure, we have find out that the deterministic trail. So we can apply the procedure to find any probabilistic trail, right? Like our procedure gives a unique trail, but if we consider some other trails also, deterministic like probabilistic, in that case we can obviously induce some fault in more number of rounds, and we can use we can get the number of trails, and using that we reduce the key space. But in that case the key space reduction won't that much faster.
Okay, thank you for the very good idea.
Any other questions or comments? If not, I have one. So could you please get back to the last slide? Yes, the last one, next one. Yes, at the bottom, you says our findings underscore the difficulty in achieving DFA protection. And so how do you think there is any hope to achieve DFA protection, or do you think it seems very hard or almost impossible to achieve such a thing?
Okay. No, that's not the case. Like as for default, the authors has the intuition that like it's a updation of gift, or in gift actually it is designed such like the hardware area, or it is lightweight, more lightweight than present, or like because of that they have introduced the bogey permutation or something, and in default they wanted to make it more lightweight. So because of that they have used linear structured S-box. But we have shown that if we use linear structured S-box, then also using the differential fault attack, it can be broken, or we get the unique trail, or we reduce the key space uniquely for some number of rounds. So our motivation is like we cannot use LS structured S-box to like for DFA protection, but we can obviously use some other techniques or other procedures for that. But if we use LS structured S-box, then that like our attack procedure, through our attack procedure we can find the unique trail, and because like using that we can reduce the key space. So LS structured S-box we cannot use for that. So this is the one thing.
Thank you.
Thank you.
If there is no any other questions, are there any other questions? No? Then I'd like to thank the speaker, Harin. Thank you. So the next talk is online. Yes. Hello?
Hello.
So, yes, okay. Then let's move to the next talk. So the next talk is modeling ciphers with over-defined systems of quadratic equations, application to Friday, Vision, Rain, and Biscuit. The authors are Furkan Liu, Mohamed Mason, and Willy Meyer. And the speaker is Mohammed Mazum. Please go ahead.
Okay, thank you. So polynomial systems are very interesting topics in cryptography in general, because the hardness of the hardness of some cryptographic primitives actually rely on the hardness of solving polynomial systems. And also polynomial systems are the main tools in algebraic cryptanalysis. And what is algebraic cryptanalysis? Algebraic cryptanalysis is a technique for analyzing the security of cryptographic primitives by exploiting the algebraic properties of the cryptographic systems. And mainly it is based on modeling the cryptographic primitives as a system of polynomial equations and try to extract information about the secret of the system by solving these equations. And cryptographic primitives, like usually such as hash functions or block ciphers, are often functions that can be modeled as polynomial systems that has a finite number of solutions. So specifically in this work, we focus on primitives that can be modeled as either determined or overdetermined polynomial systems that have finite number of solutions. And to solve such polynomial systems, there are various techniques available, but in our work, we primarily rely on the algorithms from the Grosvenor basis family. And the idea behind Grosvenor basis is to take the polynomial system and extend it to some high degree by multiplying each polynomial with number of monomials, and then use linear algebra techniques to derive a Grosvenor basis. And the complexity of Grosvenor basis is asymptotically upper bounded by a binomial function of the number of variables in the polynomial system and a degree that is called the degree of regularity. And this degree of regularity intuitively is the smallest integer d, that if we extend the system to the degree d, then Grosvenor basis can be derived using linear algebra operations. And this degree of regularity, when the polynomial system that we have with m equations and n variables is regular, then can be measured using this Hilbert power series that is shown here. And it would be the exponent of the first term that has non-positive coefficient. So this Hilbert series that we have here is actually a decreasing function in the number of variables that is denoted by m, meaning that if we increase m and keep the number of variables that is n constant, then this degree of regularity would be smaller. And what does it mean? Intuitively, it means that having more polynomials in the system makes solving the system easier. Of course, not any kind of polynomial is useful. For example, if we add a bunch of linear combinations of the polynomials that are already in the system, it's highly unlikely that it can help us solving the system easier. In this work, we are interested to find additional equations for polynomial systems that are modeling cryptographic primitives, that they are actually indeed helping us solving the system easier. So historically, AES has always been an interesting design target for algebraic cryptanalysis. And an interesting line of research was to try to find overdetermined polynomial systems that are modeling AES. And it was always an interesting problem. So first, as a reminder on how AES works. So AES operates over a field of characteristic 2 with 256 elements. And the state of AES is 16 bytes. And each round of AES has 4 types of operation. A subbyte, which is the S-box of AES and is the combination of inverse map with a linearized affine polynomial. And we have more operations such as shift rows, mixed column, and addition of round keys, which are linear. And yes, and the feature of AES that allows to define more equations is the nonlinear inversion function that is used in the S-box. So the first approach that was used to find additional equations for AES was by Kortua-Pieprzych, where they exploited the structure of the inverse function used in AES. And so the inverse function is x equal to y to the power of -1. And the idea is that this can be also represented as the quadratic equation x times y equals to 1. And the idea to find extra equations for this inversion map is that the power maps that have exponents that are powers of 2 are linear over the finite fields that have characteristic 2. So that means that if we take, for example, a variable x and raise it to the power of 2, then we still have a function in x that has algebraic degree 1. And this function over the extension field would be linearly independent from x, but when we model it in F2, it would be a linear function of x. So using this technique, then we can define 4 extra quadratic equations to model the inversion function. So what we can do is that we can multiply both sides of xy equal to 1 with x, for example, and then we have x squared times y equal to x. And although x squared times y equal to x has degree 3, when we write it as equations over F2, it's quadratic. And in other words, it has algebraic degree 2. So what we can do is that we can repeat this process and have more equations such as xy squared equals to y, x to the power of 4 times y is x cubed, and xy to the power of 4 is y cubed. And all of these are polynomials of high degree, but all of them have algebraic degree 2 over F2. And as a result, we can have 5 equations with algebraic degree 2 that can be then transformed to quadratic equations over F2. And this approach of Kortua-Pieprzych was later improved by Murphy and Robshaw. So the idea was to define new variables for each monomial that has the exponent which is a power of 2. And then the system can be modeled with the same degree as its algebraic degree. So as a result, we can define much more equations, and also we can over-define the system as quadratic polynomial system also over the extension field. And they applied their idea to AES, and in case of AES, they defined a new primitive called BES that has extended state size, and then the polynomial modeling of BES results in an over-defined polynomial modeling for AES. So in our work, we applied the similar approaches to different arithmetization-oriented primitives that have a similar structure to AES. And we generalized the Murphy-Robshaw's technique using simpler approach. And as a result, we show how to define new equations for primitives over binary fields without actually needing to modify the primitive. So the first primitive that we studied is an arithmetization-oriented hash function called Friday. So Friday has already shown to be insecure against Grosvenor basis attacks in a paper from Asiacrypt 2019. But what we do here is that we show that using our techniques of adding additional equation to the system, the complexity of the algebraic attack against Friday can be further improved. So how Friday works? Friday is constructed by using a permutation called Jarvis in Merkle-Damgard mode. And the problem here is to launch a pre-image attack on Friday hash function. So to launch a pre-image attack on Friday, what we do is that we take an instant and then we model it as a polynomial system, which has the input of the hash function and probably some possible intermediate states as variables. And the coefficients of polynomials then are determined by the known data, such as hash values or the constant that are injected in each round. So in the case of Friday, we have a polynomial system, and the goal is to recover the input x from the hash values h0 and h1. And the permutation Jarvis is an SPN design, which is inspired by the design of AES. So each round consists of inversion function and the combination of two linearized affine polynomials, B inverse and C. So as we described for AES, the inversion function can be modeled using quadratic equations that are overdefined and linearized affine polynomials. Okay, so the problem here is that we can actually model the inversion as quadratic equations, but here we have linearized affine polynomials that are only linear when they are modeled in F2, and over the field that Friday works on, they have large degree. Indeed, both B and C's that we have here are with degree 4. So here what we can do is that we can model each round of Friday as a multiplication of two linearized affine polynomials of degree 4. So to find more equations for Friday, what we have to do first is to try these linearized affine polynomials that are multiplied to each other to quadratic polynomials. And what we can do is to replace each monomial with an exponent that has a power of 2 with a new variable. So this way we can model the linearized affine polynomials as affine polynomials over the extension field. And then we can model each round as multiplication of two affine polynomials. Now, what we can do is that we can raise these affine polynomials to the power of 2, which results again in affine polynomials, but having the indices of the variables shifted because we defined variables for the powers of 2. So what we can do is, what we are doing is that now we are defining additional quadratic equations by raising each affine polynomial to the power of 2 that are visible in this table. And yes, so then we would have a system that has 4 times our variables and 7 times our equations. So it's almost twice equations as variables. Compared to the paper from Asiacrypt 2019, which was modeling Friday as a determined polynomial system that had R over 2 variables and R over 2 polynomials. And R here is referred to as the number of rounds. So to see the effect of the additional equations that we defined, we drew this plot. So although the number of variables in our model is 8 times larger than the number of variables in the attack from the previous paper, we can see that our approach is faster when the number of rounds grows, and the gap is also increasing. So the next primitive we studied is vision. So vision has a very similar structure to Friday and AES, and it uses inverse function as its nonlinear map. So this use of inversion makes vision a natural target to our technique. So each round of vision has 2 steps, which are combination of inversion function, linearized affine polynomial, and MDS matrix. So again, what we can do is by defining a sufficient number of variables, we can convert linearized affine polynomials to affine polynomials, and then equations to model each round at first have the form of multiplying linear affine polynomials before and after each inversion function, but with new variables. These multiplications are then written as multiplication of affine equations, which the whole equation is quadratic. So this way, the round function of vision then can be simplified as the multiplication of a variable and the combination of other an affine combination of other variables. And since the equations, so since this is the form of equation that we have for inversion function, then we can create an overdefined polynomial system for vision by raising various affine parts of this system to the powers of 2. So here in this plot, we see the complexity of solving overdefined systems of vision compared to the complexity of solving the system that the designers of vision used to argue the security of vision. And we showed that using the overdefined equations, we can actually improve the complexity of solving vision using algebraic approaches. And the next primitive we studied is rain. So RAIN is a block cipher that is used in the design of post-quantum secure digital signature scheme Rainier. And here we study the instance of RAIN that has 3 rounds, because the 2 rounds of RAIN has already been shown to be insecure against algebraic attacks in 2 different works. And RAIN also has a similar structure to the previous designs that we described, and it uses inversion as its nonlinear layer. So the equations that are describing RAIN are very similar with the equations that are describing Vision, Friday, or AES. What we do is that we model RAIN using 3 variables, which are x1 and x2 as intermediate variables and kappa as a secret key. And then we have the noun parameters x0, which is the input, x1, which is the output, and we have constant EIs. So this way, then RAIN can be modeled using 3 equations of algebraic 2 for each inversion function that is in the design of RAIN. So for example, for the first one, we have that the x1 is the inverse of input plus kappa plus some constant. For the second one, we have that a linear function of x1 is equal to the inverse of a linear function of x2. And similarly, the last one is that x2 is the inverse of output plus secret key plus some constant. So these equations are defined over a binary field of size 2 to the L. And they have high degree because of the linear maps. But what we can do is that we can again model them as equations over F2. And in F2, they would be quadratic equations. So then each equation that we have here would be represented as L equations over F2. And then for each variable that we have in this system, we defined L variables that are taking values in F2, because variables here are L bit, so we convert them to the 1-bit L variables over F2. And then using the standard approach that we use so far, we can define 5 equations for each inversion function, which results in 15 L equations in total. And then we have 3 L field equations for each of the variables that we have defined. But we can also, in case of RAIN, derive 5L extra equations because of the structure of the RAIN. And our approach improves the solving complexity of RAIN for the 3 different instances that is defined for RAIN. So RAIN is defined for 3 security levels, 128, 192, and 256 bits. And the instance that that offers L bits of security works over the field of size 2 to the L. And here we show that the instance that offers, we show that the complexity of solving the instance with 256 bits of security using our approach is a bit smaller than the intended security level. And the last primitive that we study is the underlying one-way function of post-quantum secure digital signature scheme Biscuit. So Biscuit is designed using MPC in the head paradigm, and it means that the hardness of biscuits solely relies on the hardness of the underlying one-way function that they are using. And in case of Biscuit, the underlying one-way function is called POVAF2 problem. So POVAF2 problem states that the quadratic equations that are derived by taking linear maps and multiplying 2 of them, and add the third one and add some constant, which results in an affine quadratic equation. If you have a set of these kind of equations, then it's hard to solve them. So what we have here is that we have a system of equations that has very similar structure to the inversion map that we used for earlier previous examples. So there is no inversion in POVAF2, but the structure of the polynomials are very similar. So it's the multiplication of 2 linear maps. So again, we can apply the same technique by raising different linear parts of the system to the powers of 2. And this way we can define extra equations for Biscuit. So in the case of POVAF2, then this additional equations does make the solving of the system easier. So in conclusion, what we did was that we exploit the structure of several primitives that have with similar structure to find over-defined system of equations that describe those primitives, and we use those equations to show that we can solve those primitives more efficiently. And we studied 4 different primitives. Friday, which for an instant fits all round, we defined 7R equations in 4R variables, and our approach improved the results from the paper from Asiacrypt 2019. And then we studied vision, which its hardness is reduced to solve an overdefined polynomial system with roughly twice the equations as variables. And this improves the complexity of Grosvenor basis attacks against vision. And then we studied RAIN, which is reduced to solving an overdefined polynomial system that has 5 times equations and variables. And finally, we showed how to solve power of 2 problem more efficiently than what is expected in the design paper. And there are several directions that this work can be further studied. So the additional polynomials that we describe are sometimes have a strong structure among them. And therefore, these structures can lead to syzygies among them in higher degrees. So there would be relations between polynomials in higher degrees. And these syzygies make solving the system harder. So an open work would be to study these syzygies at higher degrees and what are their impacts on the solving of the system, on the complexity of systems that have parameters closer to the real instances. And that's all. Thank you for listening.
Thank you for the talk. So are there any questions from the audience? Yes.
Hi, thank you for the talk. So I was wondering what your intuition is behind this work, in the sense that you start from a well-defined problem, like a square problem, and then somehow you describe it as an overdefined system of equations. But I mean, in a sense, you wouldn't expect there to be more information than, I mean, you don't create any new information, so how do you, or why would then this overdefined system be better than like a normal well-defined system?
So thank you for your question. Actually, that's a very nice question. So yes, what happens is that the polynomial systems that are defined here are not truly random, so they have a structure among them. So actually what we are showing is that this structure makes solving the system easier. So there might be cases that actually the additional polynomials are not providing new information. And in those cases, I agree that the asymptotic complexity will not be improved. So, but what happens is that adding those equations to the system actually makes the complexity, the concrete complexity of the solving of the system smaller. So it might be the case that the equations that we are adding would be added to the system later in the steps of the Grosvenor basis, but we show that, okay, we are adding them at the beginning, and we show that, okay, at the end, the degree of regularity would be smaller, so in total, the complexity would be smaller.
Okay, thank you. Like a small follow-up question, is that then, in a way, you kind of have found a better bound on the degree of regularity of the original system then? Or?
Yes, indeed.
Okay, thank you.
Are there any other questions? If not, let's thank the speaker again. Thank you. So the next talk is again online.
Can you hear me?
Yes, I can hear you.
Okay,
Yeah.
I will begin. Hello everyone, I'm Hongsen Yang. I will present our work, a new security evaluation method based on resultant for arithmetic.
Could you please share your slide? I'm sorry, we do not see your slide.
Oh, sorry.
Yes, now we can see your slide. Yes, thank you. So the final talk of this session is a new security evaluation method based on resultant for arithmetic-oriented algorithms. And the authors are Hongsen Yang, Junxion Chen, Jin Yang, Jianfeng Liu. Will give a talk. Excuse me, could you please turn on your microphone? Microphone. We do not hear you.
Hello?
Yes. Now I can hear you, but we do not see.
Okay.
Slides. Now I can hear you, and we can also see your slides.
Okay. Sorry for the accident.
Thank you.
In this paper, we propose a new security evaluation method based on resultants for arithmetic-oriented algorithms. We apply this method to 3 mainstream AO algorithms and derive the best cryptanalysis results. I would follow the outline to introduce the work. First, let's review the background of the AO algorithms. With the emergence of privacy-preserving protocols, such as ZK proofs and secure multi-party computation, traditional symmetric cryptographic algorithms are not sufficient in meeting the efficiency requirements in those applications. In response, new arithmetic-oriented primitives, including rescue, animal, and Jarvis, has been developed. Unlike the traditional symmetric algorithms, these designs operate on larger fields and focus on minimizing the number of multiplication operations. As a multiplication operation is expensive in privacy computing. Furthermore, there are many use larger S-box instead of parallel small S-box. Due to the native algebraic properties of L algorithms, algebraic attacks typically outperform other known techniques against L primitives. The security rounds of those algorithms are mostly derived from global basis analysis. However, global basis analysis fails to fully use the algebraic structure of AO algorithms. Moreover, the time complexity of global algorithms is not precise enough, leading to a lack of accurate understanding of the security properties of AO algorithms. In addressing those issues, we propose a novel analysis framework for AO primitives that is much more efficient than the existing one, making the security evaluation more accurate. We also proposed the substitution theory, which can effectively control the degree of equations when viewing resultants for algebraic attacks. Moreover, we have combined resultants with Lagrange interpolation, which effectively increased the number of rounds in practical attacks. Our result is in the table. We achieving the best theoretical and practical attacks to date, and use this new security analysis framework to re-evaluate their security. For the rescue prime, our new attack improved the existing best attack by a factor of 100, and practically attacked 5 rounds for the first time. For animal, we have also demonstrated a 8-round attack for specific vision for the first time, and re-evaluated the security of 21 rounds to be 110 bits, thereby breaking its security claim of 127 bits. And for Jarvis, we derived a practical attack for 8 rounds for the first time. Now we print some preliminaries for our new attack. The security of an AO algorithm can be based on solving the Kiko problem. The so-called Kiko problem is that for given permutation F, finding vectors of size 2 times S minus U over the finite field of size Q that satisfy the equation below. That is to say, the next U blocks of both the input X and the output Y are zero. And the resultant is a powerful tool for solving systems of equations. And we found that it is particularly suitable for solving equations in an algebraic attack of AO primitives, which is also the main idea of our evaluation framework. The resultant of f and g with respect to x is defined as a determinant shown here. F and g has common roots if and only if there exists a vector y such that their resultant equal to 0. These properties can be effectively used to solve the system of multivariate equations. Let's see a simple example. Here we have 2 equations that are defined over the finite field with 101 elements. Then we can define 2 polynomials f and g regarding to x and y according to equations. Then we can compute the resultants of f and g with respect to x. The variable x can be eliminated and a single variable polynomial with respect to y can be obtained. Then we can find all solutions of y in the equation system, which are 2, 1, and minus 1. Then by bringing the values of y back to the original equations, we can get all solutions of x. Now let's see how we apply the resultant to non-algebraic attacks against AO primitives. We focus on rescue prime to illustrate our method. Rescue prime is a family of AO hash functions, and its round function is shown in the figure 1. The round function of rescue prime consists of 3 main parts: the S-box, MDS multiplication, and the addition of round constants. Rescue prime has various institutions, and we mainly focus on the case where t equal to 3 and alpha equal to 3, which means this box performs a transformation from x to a third, and its inverse is from x to the power of 1/3. Such parameters is also the focus of Ethereum Foundation challenge. For the Kiko problem of rescue prime, one target is to find an input pair x1, x2, and y1, y2, such that the third word of both the inputs and the output are 0. First, let's discuss the construction of equations for rescue prime using forward modeling. As shown in the figure 2, when the variables pass through the structure of x to the power of 1/3 in a forward direction, it will generate a high degree. Due to the high degree in the forward direction and only a low degree when the variable in the backward direction, we introduce new variables after the S-box. Specifically, for variables in the middle, they first bypass 2 linear layer and 1 S-box. When bypassing the nonlinear layer, x to the power of 1/3, we need to introduce new variables and link them using equations below. For one round of rescue, there are 3 x to the power of 1/3 structures. So we introduce 3 variables and construct 3 equations. Each round equations is as follows. Because of the Kiko problem's constraint, the last output blocks must be 0, which leads to an additional equation. So when it comes to our round of rescue, by appropriately choosing the values of y1 and z1, we can use the bypassing the first round technique proposed in 2022. We will not detail it here. Then the entire system consists of 3r minus 2 equations and variables. This system of equations has a very strong triangular structures, and by choosing an appropriate resultant path, one variable can be eliminated with each resultant. For example, only f sub h and f sub z2r minus 1 contain the variable z2r minus 1. So compute the resultant of them and renew f sub h with the resultant can estimate z2r minus 1 from the system. Similarly, we can proceed to eliminate y2r minus 1 and then x2r minus 1. By performing 3r minus 3 resultant operations, we can obtain a univariate polynomial in x1. Using resultants for elimination will continuously increase the degree of the variables, but a spatial structure makes substitution become possible. We observe that the cube of each variable, except x1, can be represented by variables with smaller subscripts. This allows us to use substitution to control the degree of variables except x1 no more than 3. Let's take a simple example. After the first result operation, degrees of variables in f sub h may be greater than 3. Then we apply the following substitution in order. Then f sub h can be transformed into a polynomial with a degree of each variable except x1 less than 3. Algorithm 1 represents the pseudocode of our method. Given the equations construct under forward modeling, algorithm 1 returns a univariate polynomials in x1 containing the correct solution. Computing a resultant once and use it to update f sub h can eliminate one variables from the system. After each resultant, use cubic substitution to keep the degree of variables lower than 3. By continuously computing the resultants and control the degrees of variables using cubic substitution, we can effectively obtain the univariate polynomials in x1. The table 1 shows the complexity of our attack against the rescue prime under the forward modeling. We successfully attacked the 4-round rescue prime algorithm using forward modeling, but failed to attack 5-round rescue prime due to the memory overflow issues. So to further reduce the time complexity and attack a higher round, we also propose to use SFTM modeling shown in the figure 3, where SFTM stands for start from the middle. The core idea behind SFTM is to introduce variables in the middle and then construct equations in both directions. Similar to the forward modeling, when performing forward modeling, we introduce a new variable each time when there is a x to the power of 1/3 structure. Similarly, when tracing back through the x to the 3rd structure, we add new variables as needed. The party of the number of rounds R will result in different equations modeling. Here we focus on R is an odd number. The form of the equation is as follows. It is clear that these equations also have a distinct algebraic structure. Each variable's cubic term is only related to variables with lower or higher subscripts. Similarly to the forward modeling, each resultant operation can eliminate one variable. We take a simple example. Variable x2 only appears in f sub l and f sub x2, and the variable z2r minus 1 only appears in f sub h and f sub z2r minus 1. We can compute the resultant of them and then renew the equation system to the right side. Variables x2 and z2r minus 1 are eliminated from the system. Algorithms to demonstrate the process how SFTM modeling uses resultants to eliminate variables. It eliminates variables from both ends towards the middle using FL and FH, and control the degree of variables using cubic substitution. Ultimately, algorithm 2 returns two polynomials, FL and FH, in variable xr minus 1, yr minus 1, and zr minus 1. Since there is one more variable than equations, we can assign a value to xr minus 1 in advance. And ultimately, we obtain two bivariate polynomials in yr minus 1 and zr minus 1. So the next step is to compute the resultant of FL and FH. However, as the number of rounds increases, the resultant of F sub L and F sub H can lead to significant memory consumption. To address this, we choose to use Lagrange interpolations. By assigning multiple values to yr minus 1, we compute the resultant values of f sub L and f sub H, which is equal to assigning a value to the univariate polynomials in y at the end. We then recover the univariate polynomials using those interpolation points. Notably, applying Lagrange interpolation to solve the final resultant step allows us to parameterize the most time-consuming process, which is significantly improving the efficiency of the attack. And at last, we use the half GCD algorithm to solve the univariate polynomial. The attack complexity against the rescue prime under the SFTM modeling is shown in the table 2. It can be seen that SFTM modeling has reduced the complexity of the attack and successfully attacked the 5-round rescue. The experiment results are shown in the table 3. We use the same prime number published by the Ethereum Foundation. For 5-round rescue, we have used 16 threads for interpolation calculations, which significantly improve the efficiency of the attack. And for 4-round rescue prime, we also improve the attack efficiency by more than 100 times. Using the analyze framework, we give 8-round correlation for animal in a 15 bits prime field for the first time, and improved the attack efficiency on 7 rounds by 15 times. And for Jarvis, we derived a practical attack for 8 rounds for the first time, and significantly improved the attack efficiency for 6 rounds. Now let's have a brief summary. Our resultant-based evaluation framework against the AO primitives consists of the following 4 steps. The first step is to construct a system of equations using forward modeling or SFTM modeling method. Then combine the resultants and the substitution to eliminate variables in a specific order, and finally get to bivariate polynomial. After that, we use fast Lagrange interpolation to recover the univariate polynomial. And last, we find all roots of the derived univariate polynomial. Under the security analysis framework, many existing algorithms have security flaws. Below are some possible directions for improvement. To prevent the resultant-based analysis method, one may set more rounds to enhance the security of AI algorithms. In addition, Doing the structure of x to the power of 1 alpha as a nonlinear function often leads to variable isolation properties, which means one resultant operation can estimate one variable. Besides, this structure will lead to alpha substitution, which makes the algebraic attacks based on resultants combined with substitution will be more effective. So, some more secure nonlinear functions are needed. For example, big S-box over extension fields may be effective. And for security, we think replace the round constant addition to the short operation may make it hard to build equations. That's all. Thank you.
Thank you for the talk. So are there any questions from the audience? If not, I have one question. So I am not an expert of arithmetic-oriented schemes, so I may be asking a stupid question, but do you think is there any relationship between such a technique like yours and some cryptanalytic technique on multivariate public key crypto systems?
Thanks for the question. We think our method in algebraic attack may only suitable in the AO primitives because this kind of primitives has a very strong singular structure, but in the general multivariate equations, it will be hard to use resultant to eliminate variables. For example, for number of n equations, you may need to n minus 1 resultant operations to eliminate one variables. That's my answer. Thank you.
Thank you so much. Yes.
So in your conclusion, you said about big S boxes over extension fields. Could you expand on that? What you meant? Could you hear me? Yeah.
Yes. Could you hear me?
Yes. Yes.
Because we have studied the algorithms like X hash 8 or X hash 12, and they have used a nonlinear structure big S box, and we found if we use a forward modeling, it will be hard to use resultants to eliminate variables. For example, we may need to use 2 or 3 operations and can only eliminate one variables in the big S box. That's all.
Thank you.
Are there any other questions? If not, let's thank the speaker and let's thank all the speakers of this session again. Thank you.
Okay, thank you.
So this is the end of the session, and the next slot is coffee break.